Anyway, we can separate the whole cloud layer into different sub-layers to capture the CER variability. And then we put them into reduced transfer model and simulate the satellite observation. And then we can conduct MODIS-like retrievals using those spatial combination and see how the retrieval cloud properties like COT and IWP are impacted. And here we use exactly the same MODIS collection 6 ice cloud model, and we consider different kind of uncertainties in our retrieval. So let's look at COT retrieval first. So for each panel, you have the x-axis means different profiles. You have very homogeneous clouds in the middle, and you have severely inhomogeneous profiles on the two sides. For this side, you have small particles near cloud top. On this side, you have larger particles near cloud top. So you can see that for here, the arrow bar means retrieval uncertainty, and the different colors means different retrieval using different channels. So you can see that for COT retrieval, there's very little impact from the ICVH impact. So you can see that the curve is always flat. It is independent of ICVH. But for IWP, that's a totally different story. So for example, here, when you have small particles near cloud top, you can find that the retrieval underestimates the IWP by maybe 30% or even more. On this side, you have larger particles near cloud top, so the retrieval overestimates the overall IWP. That's not a big surprise because the MODIS use shortwave channels, which are more sensitive to the upper parts of the cloud. So that tells you this feature. So if you compare between the different retrievals using different channels, you find that the 3.7 micron, which is the yellow curve, gives the largest on BIOS. That's because that channel, ice crystals in that channel is the most absorptive one. Okay, now our question is how this impact could be for global monthly mean ice cloud records, for example, the MODIS level 3 products. To answer that question, we have to use realistic data from CALIPSO and CloudSat. We use 1 year data from 2C eyes and 2B geoprofile LiDAR data. And then we can get the annual average CER profile from this data set. And as you can see, those different profiles indicate clouds with different IWP. For example, for very thin clouds, you have small IWP, and here's the profiles for those clouds, which is you have a little bit difference between the particles near top and near bottom. But when the cloud goes thicker and thicker, you have very complicated profiles. Eventually goes to this, the red curve, which is very inhomogeneous. The particle size increase very rapidly when you go deeper into the clouds. And then we can use a very simple linear regression to calculate the slope of the CER for each profiles, which is actually the black dots. In this plot, the y is CER profile slope as a function of IWP. So and then we can use a smooth curve to fit this plot, and then we can get this relationship is very important. With this, we can estimate if we know the overall IWP, we can estimate how the particle size distributes in the whole cloud layer. And then we need to find out the relationship between the reference IWP with the retrieved IWP. To do this, we start from a randomly selected IWP and COT pair. And then with the IWP, we can, with previous relationship, we just derived this equation. We can estimate the vertical distribution of CER. And then we put them into reduced transfer model and get the simulated observation, and then conduct MODIS-like temporal retrieval by assuming the cloud is homogeneous and get the biased retrieved IWP. And we get this. So we can repeat this process again and again using different IWP and COT pairs and using different geometry. So, for example, this plot we use 1.6 to get this relationship. The x-axis reference unbiased IWP, and here is MODIS like retrieved IWP. You can see that the MODIS IWP is always underestimates on this side. That's because that is true because according to the CALIPSO CloudSat observation, larger particles is always close to the cloud bottom. So that's consistent with our previous sensitivity study. And the different colors here indicate different solar length angle. You can see that when you have larger solar length angle, the MODIS gets larger bias for all of the three retrievals. So now with this relation, we can estimate how the unbiased IWP could be start from the MODIS product. So here I show the MODIS IWP retrieved from 2.1 microns channel. Here are two different months, January and July in 2007. And here is the estimated unbiased IWP. So what we do here is just replace the MODIS IWP by the estimation, the unbiased IWP. We just replace this variable here. If we take the differences, we can find that here's the MODIS minus estimation. You can see that this is the absolute difference. You can see that they are all negative, which means MODIS always underestimates the global ice water path. But you can see there are some spatial structures here. For example, in January, in northern hemisphere, you have larger bias here. That's because the solar length angle is larger in January in northern hemisphere. The same thing happened in southern hemisphere in July. That's also because of the solar length angle issue. And if you look at the differences in terms of percentage, you can find that for global average, the MODIS underestimates by about 30%. But for some local locations, for example here, the uncertainty, the bias can up to minus 50%. So the ICVH could have very large impact on global IWP on the level 3 data. Here's the zonal mean of the MODIS retrieved IWP and estimation. So the MODIS is the solid curve and the dash curve is the estimation. You can find that the estimation is always larger than the MODIS, and different colors indicate different channels. But here, one thing I want to emphasize is the 3.7 IWP is the lowest product. But here, we just assume that ICVH is the only reason cause the retrieval differences between the three. However, if it is true, if ICVH is the only reason, then we should end up with almost identical retrievals after correction. But it is not. You can see that after correction, the 3.7 is still the lowest part here, also here. So that means ICVH is not the only reason for the retrieval difference between the three. So one possible reason is that because the cloud phase detection. So there are a lot of maybe mixed phase clouds, or there are a large fraction of clouds with maybe they have super cool liquid water on the cloud top, but below that there are all ice. Could be some cloud like that, so that can have a large impact on 3.7 retrieval. But that requires further investigation. Okay, finally, let's look at the cloud radiation. So here, the left one shows the outgoing long wave radiation at TOA, and the right one shows the short wave. So you can see that here, the first row shows the calculation from the MODIS only, and the lower part shows the MODIS minus calculation using the homogeneous clouds by taking into consider the CER profiles. So you can see that although you can find some spatial structures here, but if you look at the magnitudes, they are very, very small. They are in between negative and positive 0.5 watts per square meter, something like that. So I have to say that difference is quite small. So the ICVH have little impact on cloud radiation. So this is quite small in comparison to other uncertainties of clouds. For example, if you just simply replace cloud particle shape from one to another, for example, you change the shape from plates to something others like column. That will tell you very huge differences in terms. If you look at the flux, that can have maybe 20 watts per square meter or even larger. So this 0.5 watts per square meter, which is very small, very marginal. Okay, so for the summary for the first part, ICVH could lead to relatively large IWP bias and little impact on COT and flux biases. So you can see this this conclusion from this figure. So here you have gray bars here, which means the IWP bias. So this is global average. You have for MODIS, the underestimates global ice water pass by minus 35% for global ice cloud over ocean. But for very thin clouds, the underestimation is not that strong, about minus 10%. With the cloud goes thicker and thicker, for very thick clouds, they have underestimation by minus 50%. And in terms of radiation, here the blue ones short wave, yellow ones long wave, and red one is the total. So for global average, the radiation difference is less than 0.15 watts per square meter, which is very, very low. Even if for very thick clouds, the difference is still very low, about less than 0.3 watts per square meter. Actually, we have a manuscript about this study, and we have submitted to JGR, and we get some very positive feedback from the reviewer. So hopefully, it will come out in next month, hopefully. Okay, so part 2. You mean the uncertainty? So I didn't look at that in the standard MODIS product, but I guess in terms of IWP, because in MODIS they didn't retrieve IWP directly, they retrieve COT and particle size, and the IWP is actually a product of that two variables. So you have they provide the uncertainty for COT and uncertainty for particle size. So if you combine them together, I think the typical uncertainty for IWP could be about 50%, 30 to 50%, I have to say. But I'm not 100% sure about that. Mm-hmm. Yes, that's right. Good point. Okay, part 2. So in this part, this is actually a ongoing project, so which is using a joint observation from infrared and microwave sensors to retrieve ice water pass and cloud top heights. So as I talked before, individual instruments have its own limitations in information contents. It is sensitive to different parts of clouds. So if you stick with one instrument, it cannot cover the whole dynamic range of clouds. So the common sense is just combine them together. For example, if you use infrared sensors, it cannot handle very optically thick clouds. For microwave, it is not sensitive to very thin clouds. So if you combine them together, you can overcome all of these shortcomings. Here's another example of how the combined retrieval works. So here's the retrieval uncertainty in terms of IWP as a function of cloud optical thickness. So you can see that if you use infrared only retrieval, which is the blue curve, you have small uncertainty if the cloud optical thickness is low, but the uncertainty goes larger and larger when you have thicker clouds. And for the microwave, that's different. When you have small optical thickness, you have larger uncertainties from microwave. But when the COT goes larger, the microwave gives you lower uncertainty. So if you combine them together, which is a red one, because of the large information content you have, which gives you the lowest retrieval uncertainty. Another advantage for the combined infrared and microwave is you have consistent daytime and nighttime algorithms, so which is much better for investigative cloud diurnal cycle. So for models, we have developed two models. One is for infrared and one is for microwave. For infrared, because I don't have enough time to go through the details, but we have two papers describe the infrared model and the retrieval algorithm. So it is an optimization-based cloud retrieval algorithm. We retrieve cloud optical thickness and particle size, and also cloud top height using the MODIS infrared channels. And we have applied this method to the MODIS global MODIS data. And here you can see the comparison between the MODIS standard product versus our retrieval. So they are very consistent. This is 1 month of COT, and here's cutoff height. And for microwave, Dong and Jay actually developed a microwave model for the microwave humidity sounder, MHS. So they found some relationship between the ice water path with the microwave, high frequency microwave observations. So they have developed a empirical model for those microwave channels higher than 150 gigahertz and some sounding gigahertz channels. But one difficulty we have to handle is, as I talked before, when you combine the infrared and microwave together, they have totally different spatial resolution. So for microwave, they have, for example, the FOV is about 20 kilometers. But for infrared, they have 1 kilometer nadir at nadir point of view. So in this case, so here is an example of how the infrared observation change as a function of CER and COT. You can see that there's a huge curvature here. So if you just simply average the infrared observation for the whole domain, you get a very huge nonlinear effect. So that can give you biased retrieval. So we have to handle this. So what we do is we developed a so-called IWP beam method. Again, for this FOV, assume that you have n small pixels for infrared and a super large FOV for microwave. And here's the total number of observations we have for this. For infrared, we use 6 MODIS infrared channels, 8.5 through 14 microns. And for microwave, we use 2 ATMS high frequency channels, 165 and 183 gigahertz. So here's a total number of observations we have. For step 1, we conduct infrared-only optimal estimation retrievals for each pixels. So here we just use infrared observation only. So in this case, if we write the equations from infrared, we can retrieve cloud properties for each small pixels. So we retrieve IWP and cloud top heights for each pixel. This is step 1. And step 2, we can try to create some strategies here to group those subpixels. For example, here, this is currently this is a strategies we are currently using. But maybe in the future we can find some better way to do this. But anyway, we group the small pixels by the infrared retrieved ice water path. So for example, we can separate them into 7 different categories, smaller than 20, 20 to 40 gram per square meter. So with this, we can separate the pixels to different groups. And then we can safely average the inferred observation for each group because we assume that each group, clouds in each group have similar cloud properties, so there's no nonlinear effect there anymore. And then we can update the inferred retrieval with combined infrared plus microwave observations. So this time we have average infrared brightness temperature for the 7 beams, and times the number of IR channels, and the microwave observation for the whole domain. And this time we can write the closed equations like this. The first one is the infrared only equation for each of the beams. And the second one is microwave. The whole domain observation is actually we assume that it's a linear combination of each part. So we know the fraction of each part from infrared, so we can have this equation. And the total fraction is equal to 1. And with this, we can use optimal estimation to retrieve cloud properties for each IWP beam. So here's an example. Here I use 3 ATMS footprints, for example. Here on the left side, this is the step 1. We use inferred only retrieval for each subpixels. This is the infrared only ice water path. So and after the updates, we get this. So eventually we have a hybrid spatial resolution ice water path retrieval. So you can see that here shows the ice water path distribution for different groups. So for example, if you have category through 1, 2 through category 4, something like this, the gray one is the infrared only. The pink one is after the update. So you can see that for cloud pixels, very small ice water paths, the infrared dominant. So even if you have updates, there's no difference between the two. But when you have category 6 and category 7, which means the ice water path is large enough, the infrared started to saturate. So in that case, the microwave dominant. So you can have a huge difference between before and after the updates. Here I'll show a case study for this. This is a MODIS granule over ocean, over open ocean. So most of the part of this granule is covered by ice clouds. For example, here. There are some very thick deep convection here in this region, and there are also some thin cirrus here. Maybe it's not very clear for you. And for this part, there are liquid clouds. So we apply this measure to this granule, and you can find that the difference between using different channels. Firstly, we use microwave-only retrieval. So this retrieval, you have very nice retrieval near the deep convection center for this region. You have very nice retrieval. But for this region, you have thin cirrus. The microwave has no sensitivity for those very thin clouds. But if you use infrared only retrieval, this one is the infrared only. We use the MODIS infrared channels. So you can see that for thin cirrus clouds in this region, it has performed quite well, but it starts to saturate around IWP close to 200 or 300 grams per square meter. And the last one is the standard MODIS collection 6 retrieval. It has some good retrieval for thin clouds, but for deep convection, it still goes to saturate. Maybe it's also could be caused by the vertical heterogeneity as we talked before. But the thing is, if we use infrared plus microwave retrieval, which is this one, we have a very nice retrieval for no matter what kind of cloud it is. For very thin cirrus clouds in this region, it's close to the infrared only. But for the deep convection, it's much better than this one, and it's close to the microwave only. So that's very nice. And here's the curtain plot comparison along the CloudSat CALIPSO track. So you can see that here's the CALIPSO CloudSat track. So we have different retrievals. The red one with uncertainty arrow bars is the combined retrieval, and the dark black line shows the CloudSat standard product, and the dark blue one is inferred only, and the light blue one is the MODIS standard product, and the yellow one, this one, is the microwave only. So you can find that for very thick clouds in this region, the Jones retrieval, inferred plus microwave, is very consistent with CloudSat and microwave. But for this region, you can see that the microwave only fails. They have very low retrieval for this region. But the combined retrieval is very close to the inferred only and the MODIS. So which means the Jones retrieval combines inferred and microwave can handle the very wide range of cloud dynamics. Okay, as a summary here, we have developed the Jones inferred and microwave retrieval to retrieve ice clouds, optical ice clouds, water path, and the clouds top height. And we developed a new IWP beam method to handle the subpixel variability as I talked before. And at this time, we just applied this method to collocated ATMS and MODIS instruments, but in the future we will change our infrared model to WIRS also. So once I have done that, we can apply this method to MPP, ATMS, and WIRS instruments. Yes, I think I'll finish here. So I'm glad to take any questions.
Questions? So I do have one. So how do you adjust the weight for the joint retrieval compared to the infrared and microwave?
Yeah. So the reason is if you look at here. So if you look at here, the weight is actually the sensitivity of each model. So once you have, for example, once you have very thick clouds, the infrared observation is started to saturate. So there's no, if you calculate the Jacobian of the infrared observation as, for example, D brightness temperature, D cloud properties, it is almost zero. So when you put them in the optimal estimation, there's no sensitivity for infrared. So in that case, the microwave dominant. Yeah.
Let's thank the speaker again, and we ramp up. Thanks.